Before farmers invest in or take on alternative production practices, it is important to be familiar with the growing body of science-based research to help support transition toward new approaches. With all of the recent attention being paid to soil health and what farmers might do to achieve 4 core principles of soil health on their farms, what does locally generated research tell us about what is possible in cotton production systems in the San Joaquin Valley? These 4 principles are minimizing soil disturbance, maximizing biological diversity, having living roots in the soil as much as possible, and keeping the soil covered with plants and plant residues at all times. In this video, we summarize important findings and outcomes from a unique long-term study conducted in the heart of the San Joaquin Valley's cotton growing region in Five Points, California, beginning in 1999. Our study site is the only California research location in which the key soil health principles of reduced soil disturbance and soil surface residue preservation have been coupled with cover cropping as a means to increase and maintain soil carbon and soil health. Our site is one of 124 long-term experiments included in a North American study by the Soil Health Institute to compare and make recommendations on the best indicators, metrics, and monitoring techniques for assessing soil health. When our project began in the fall of 1999, we selected cotton as a rotation crop with tomatoes because both crops were economically important and commonly grown in the west side San Joaquin Valley region. Because there is often considerable variety in practices and terminology used in describing reduced disturbance tillage, it is important to very precisely describe the specific disturbance operations that were used in the study for clarity and good understanding. The overall study compared 4 management systems each year for each crop. The systems we decided upon represented our best approximation for standard or conventional tillage practices without cover crops that were commonly used for cotton and tomato production throughout the San Joaquin Valley. Conventional practices included full area disking, subsoil ripping, redisking, listing beds, and dry mulching the soil with a Lilliston implement ahead of cap planting into moisture for cotton. Another system in the comparison was a conventional tillage system that included a winter cover crop that was incorporated as a green manure in the spring prior to summer crop planting. We designed the 2 alternative systems based on the general principle of reducing disturbance or soil tillage to the greatest extent possible. The 2 summer crops were established directly into existing surface residues using a 6-row no-till John Deere 1730 planter for cotton and a specially modified no-till transplanter that was fitted with a large cutting coulter ahead of a double disc opener transplanter shoe for tomatoes. We explored different approaches for generating high residues. Some practices deliberately generated and preserved surface residues, including no-till cover crop seeding into residues that was done with a John Deere 1560 or a sunflower no-till drill. Other practices used various cover crop and residue choppers, including a buffalo stalk chopper with flat, sharp chopping blades to cut residues and cover crops in about 7 to 8 inch sections. Also, different cover crop termination tools were evaluated, including flail mowers and a McFarland stalk chopper. Residue cutting straight coulters were also used in front of both liquid and dry fertilizer injector shanks to increase efficacy of fertilizer applications. Early on, minimal weed cultivation was done for tomatoes using special high-residue cultivators such as the Sukup cultivator that is shown here. But then we stopped that practice. Roundup-ready varieties of cotton were used, combined with the herbicide applications. As the study progressed, the original beds were not reworked between crops in the no-till systems, so they eventually became essentially flat. It is important to point out that even during the early years of the study, surrounding farmers were already experimenting with a variety of what are now widely called minimum tillage approaches. These included use of cover crops, in part due to the adoption of subsurface drip irrigation. And thus they relied more on the use of reduced pass tillage implements, such as the Wilcox AgriProducts Performer and the Eliminator, and New World Tillage's Optimizer implements. These practices, however, still performed large-scale, full disturbance tillage and soil working, but with fewer passes across the field. Perhaps the most important lesson learned in the first few years of no-till cotton was the utter importance of getting a good, vigorous stand of plants established in the field. Care and attention to detail on planting day were needed to assure good, productive cotton plant stands. This entailed careful setting and adjusting of the row units, of residue managers, of depth gauge wheels, and of seed trench closing tools on the planter. Each spring during planting, farmers are presented with different and often unpredictable conditions. Surface soil layers themselves are undergoing change, and in the alternative systems are likely to improve over time. Therefore, it is important to be flexible and unrushed when it comes to planter setup and adjustment. Residue managers ahead of planter row units are generally designed not to push or gouge residues out of the way, creating trenches, but in contrast are useful in scratching the soil surface and lightly moving residues to the side. The watchwords for successful no-tillage cotton seeding are care, flexibility, and attention to detail, all of which are required under the new and variable conditions each year. Due to early problems between 2000 and 2009 in planting and cotton stand establishment in the no-till with cover crop system, yields for the conventional or standard till cotton systems during that time were about 10% greater than the no-till yields and 4.8% greater for the no cover crop systems. Between the years 2005 to 2009, however, yield patterns were inconsistent. By 2010 through 2013, however, there were no yield differences in cotton among the systems, indicating progress in the all-important requirement for success in achieving adequate plant stands early season. In addition to reducing the volume of soil disturbed with no-till, we feel it is equally important to preserve surface residue cover, which is indeed another important principle of soil health management systems. Frequent monitoring of percent residue cover throughout the study's duration indicated, not surprisingly, that there were major differences in surface residue amounts among the tillage and cover crop systems. The standard tillage system with no cover crop typically had very little, or less than 5% residue cover. The standard tillage with cover crop system had typically less than 25% cover, and the no tillage without cover crop had between 50 and 75% residue cover, which tended to be intermediate. And at the other end of the continuum, the no-till with cover crop had generally over 90% surface cover. The cover crops were typically seeded by November 15th of each fall and terminated around March 15th of the following spring, accounting for a growth period of 120 days. Thus, the period of actively growing biomass, solar energy capturing green ground cover, and living roots in the soil increased by about 90 days in cover crop compared to winter fallowed conventional systems. Preserving living roots in the soil for as long as possible throughout the year is another important principle of soil health management. Given the changes in residue and soil disturbance we observed at 5 Points, it is not surprising that we also measured dramatic changes in several indicators of soil health. During the 21-year course of the study, an average of about 2 tons of cover crop dry biomass, or organic matter, of which about 40%, or 17 tons of carbon, has been added to the 2 cover crop systems, relative to the bare, fallow, conventional systems. This addition of 35 tons of organic matter was achieved with about an additional total of 16 inches of supplemental irrigation water that was applied at various times during the project to the cover crops. Soil aggregate stability class was measured most recently in 2019, and it increased with no tillage and cover crop, yielding a value of 5.7. Individually, no tillage at 3.7 and cover crops at 3.6 improved aggregate stability ratings compared to the control or conventional standard tillage no cover crop system that had a stability score of 2.2. For reference, a stability reading of 2.0 corresponds to 50% of the aggregate's structural stability being lost within 5 to 30 seconds of wetting. Differences in soil aggregate stability that now exist between the systems are dramatic, as seen here with the no-till with cover crop soil on the left and the conventional no cover crop soil that disintegrates right before our eyes on the right. No tillage also reduced the time for water to infiltrate into the soil, regardless of whether cover crops were added. Combining the no tillage with cover crops most reduced infiltration time. The orders of magnitude differences in infiltration that were measured, with an average of 27 minutes taken for the 3rd and 4th inches of water to infiltrate for the standard tillage no cover crop system, compared to 45 seconds for the no tillage cover crop, are remarkable and indicate that considerable improvements in water infiltration and movement may be achieved through the combined use of cover crops and no tillage. Additional changes and documented differences in several soil biological health indicators, including the abundance and relative composition of various groups, including soil fungi, nematodes, and macrofauna, have also been recorded in various scientific publications that have come from the study. Perhaps surprisingly, while soil carbon has tended to be enriched in the top foot or so of soil, we have not measured increases in carbon when determinations are made over an entire 3-foot soil profile depth. From 2016 through 2019, we also investigated how the long-term use of reduced disturbance and cover crops influence soil moisture during the winter cover crop period. Our findings indicate that the combination of these practices actually resulted in greater soil moisture content compared to the traditional management of fallow standard tillage. Another related and important outcome of our long-term soil health cotton study in 5 Points is the recognition that major changes take time. We did not see changes in many soil health properties or indicators during the first 8 or actually 10 years of our study. In addition, our agronomic skill set, or our ability to improve the farming and productivity aspects of the alternative no-tillage and cover crop systems, also took time. We didn't succeed in achieving economic yields during the first few years of the study. This indicated that, for many people, there may be a learning curve in figuring out how to best handle residues, how to successfully terminate cover crops, and establish vigorous cotton plant stands. Ultimately, however, it is possible to improve and perfect practices to levels that will yield satisfactory economic outcomes for farmers. Overall, however, the research that has been underway in 5 Points for now over 20 years sheds light on what might be achievable with soil health management systems for cotton in the San Joaquin Valley. After this sustained period of consistent soil health management involving reduced soil disturbance, surface residue generation and preservation, and the use of cover crops, overall soil function improved dramatically compared to standard practices. Our findings indicate that dedication to the now widely touted and highly visible principles of soil health in ways that are uncommon in current production systems in the region results not only in changes in several soil chemical, physical, and biological properties, but also in the ecological environmental services that the soil provides. The benefits of reduced disturbance and cover crops include higher soil structural stability, increased water infiltration and storage, higher percent green cover throughout the year, increased surface cover protection, resulting in reduced soil water evaporation and greater biodiversity. Our findings from this unique study site in one of the historically most productive agricultural regions of the world clearly affirm the value of using the core soil health management principles of conservation or regenerative agriculture to improve soil function and to increase climate change mitigation. We conclude that cover crops had more of a role in influencing soil properties and function than reduced tillage alone, but that it was the combination of these practices that consistently had the greatest positive effects. The comprehensive nature and time span of our work provide a unique and practical demonstration of how much potential there is to transform current management practices to greatly improve the function and resiliency of soils in our region. The remarkable improvements in soil health that we observed were not, however, easily achieved. They involved considerable attention to detail, particularly with respect to the importance of planter equipment setup and adjustment and cotton stand establishment. We are aware of few who are adopting these practices in San Joaquin Valley annual crop fields. Yet, from a policy perspective and from the public at large, there is growing desire for environmentally sustainable production systems with healthy, functioning soils as their foundation. It is increasingly realized that reliance solely on synthetic, non-renewable inputs and high disturbance practices is not leading to the farms that can be sustained without substantial harm to the environment and the people who work and live there. Our results suggest that San Joaquin Valley annual crop farmers could greatly improve not only the function and efficiency, but also the sustainability of their production systems by adopting reduced disturbance, residue retention, and cover cropping practices. Preventing further degradation of our soils is less expensive than having to implement remediation practices that themselves are not always that effective. The common good that would result from achieving such sustained ecosystem improvements rightly needs to be borne by our food production systems at large, not just by farmers themselves. Consequently, market and outcome-based mechanisms to enable farmers to change are going to be needed.